Welcome to the course on fundamentals of MIMO wireless communications. Now we are studying the large scale propagation model. What we have seen in the previous lecture is the path loss or the signal attenuation due to separation between transmitter and receiver, and what we have said is the received signal strength at the receiver or the average received signal strength at the receiver is inversely proportional to the separation distance raised to the power of a certain exponent, and that is what is the last expression as we have seen. So, what we were seeing in the previous expression is for the 2-ray model, where we had seen the path loss exponent is d raised to the power of 4, because when we do in the dB scale there is 10 log of d raised to the power of 4, and that 4 has come here as 40 log d. What we also said is in practical environments, these numbers, instead of being such nice numbers as 2 and 4, as being 2 and 4, these numbers can be any other numbers. Yeah. So, as we continue to look at these particular expressions, what we see is as we have just described, path loss at a distance d is inversely proportional to d raised to the power of n, and of course normalized by d0, and hence you could write PL in decibels as path loss at d0, that is the close-in distance. And what we have seen is one could measure the PR at received d0, that means received signal strength at d0, and plus the 10 NP, that is the path loss exponent of log of t by d0. What we see below is for specific environments, how does this path loss slope or this exponent vary. For free space, we have already seen this path loss exponent is 2, whereas if we take a typical urban cellular radio environment, it varies from 2.7 to 3.5. So, these, as the numbers indicate, there is a range of variation. These numbers are not really fixed, they have to be measured, and through curve fitting with these formulas, these numbers have to be come up with. These numbers would also depend upon the frequency. In the shadowed urban cellular region, that means when there is a lot of obstruction between the transmitter and the receiver, you would get numbers in the range of 3 to 5. In building line of sight, that means when you are inside a building, between 1.6 to 1.8. So, as these numbers are less than 2, this indicates kind of a waveguide effect, typically like a corridor where there is like signals are guided towards one direction and losses less than 2. Obstructed building, that means inside a building, but there is obstruction, for example, separation walls, partitions, racks, almirahs, many other things, as typically happens inside a building. Your path loss exponent could go between 4 and 6, and in factories it could range between 2 and 3. And free space reference distance, as was mentioned earlier also, in the large coverage area it could be 1 kilometers, in small coverage area it could be 100 meters to 1 meter. This would also depend upon the wavelength of operation as well as the size of the antenna. This particular slide shows the path loss expression as given by 3GPP, which is again a very practical model from measurements. So, what we see if we try to read this expression, it is showing distance dependent path loss. So, this is the distance dependent path loss expression, which we are seeing out of many other parameters. So, L, which is the loss parameter, is indicated by I, a particular variable, plus 37.6 log base 10 of R, where R is in kilometers. Now, we have to read this very carefully and should not make mistakes. Typically, this D, as we were mentioning earlier in such an expression, is in meters, whereas in this particular expression it is given in kilometers. So, if the separation distance is 100 meters, we have to write 0.1 in this particular case. And as can be read from this particular value, the path loss exponent would be 3.76, because 3.76 multiplied by 10 would give 37.6. The first part, which is I, is described below as 128.1 in the 2 gigahertz band. Now, if you change the frequency to 900 megahertz band, one would have to use 120.9, because what we have seen in the free space propagation model, the received signal strength is dependent upon the wavelength or the frequency of operation. In these models, everything has been encapsulated. So, that means there is no antenna gain reflected. I captures the effect of frequency and all possible losses at that particular frequency, and R is the separation distance. So, once again what we can see, the distance dependent path loss, what we are encountering over and over again is the path and distance. So, we would like these expressions to be dependent only on distance as much as possible, and all other parameters to be captured inside the model, so that it is not visible anymore, to make the models as simple as possible. If we move down further and try to look at some other models which are known, for example, indoor office test environment, it looks more complicated, but there is a fixed loss which is 37 in dB, and the path loss exponent as appears in this is kind of 3, because 3 multiplied by 10. N is the number of floors in the path. So, basically if the transmitter is in the first floor and the receiver is in the second floor, so there would be value of 1 for N. L in all cases would be greater than free space losses. So, that means these are this loss that is present over here is of course much greater than free space loss. So, this is a complicated formula which is for indoor office test environment. If we move on to the next one, which is like outdoor to indoor and pedestrian test environment model, there these losses or this loss expression again in dB, right, it's mentioned it's in dB, would be given by this particular expression, where we can see path loss exponent is kind of 4, and there is 4 times 10 is 40 log base 10 of R plus 30 times log base 10 of F. So, this particular model captures the frequency of operation, plus there are fixed losses which could be due to antenna and coupling and many other scenarios. If we go to the vehicular test environment, we also include the base station antenna height above the rooftop level and the frequency of operation. So, there is a various different models, but what is common in all of these models is R, that means the separation distance between the transmitter and receiver. So, in this particular model R is in meters, in this particular model R is in kilometers, and so on. So, we have to be very careful with these particular models. Now, with this we move on to the discussion where we are not limited just to path loss. Now, we move on to the next part of large scale propagation model, that means shadowing. So, why do we need shadowing? We need shadowing because the path loss model, as we were seeing, it does not capture the environment clutter. This sentence is partially true because we will again draw the transmitter and we will draw the receiver. So, first let us take a scenario where there are probably one hill, that means a hilly region. So, there would be one line of sight, possibly one reflected path, and from the ground one from the hillock. So, this particular scenario will create a particular exponent of t. Now, if we move beyond and consider a situation where there are a lot of buildings around, there could be a lot of trees in the obstruction path, and so on and so forth. So, there would be foliage losses, things would come in, they would be reflected. So, definitely the value of NP would be different, and that is kind of captured in the path loss model. Now, whereas if we take the same scenario into account, and instead of proceeding in this direction, if we start proceeding in this direction, we might encounter a different situation. For example, there could be lot of trees around, there could be a water body, and there could be a lot of more buildings around. So, the whole propagation environment here is different from the propagation environment in here. However, we are talking of the same radiator. So, in this area, in this big area, if we look at this and we are trying to capture the propagation effects or the model, what we would like is to use a single value of NP in this whole area. This is very, very important. And the received signal strength as a separation between transmitter and receiver, as you are seeing, is given as PL of D or PL of R. Now, when it is given as PL of D, that means what we are concerned is with path loss as a function of separation distance between the transmitter and the receiver. This distance could be in this direction or it could be in this direction. It could also be in the other direction or any other direction in this area. So, if we have to capture this whole area with one single value of NP, we would not be able to capture the local variations as could happen in different directions. So, what is typically done is for path loss parameterization, we would go to a certain distance d, do a lot of readings over here, take the value and use and store the average. Then we would go to another direction, distance d, take the value and go and do the similar thing across the whole area in different directions, and what we get is the average path loss as a function of d, and it is also known as the area mean as a separation distance, function of separation distance d. However, if we have to do a prediction of signal strength being above a certain threshold, what we need to do or what we need to capture is local variations in these different directions. Clearly, in this particular example, whatever we see in this direction is not the similar propagation environment in this direction. So, we would like to use the path loss model for an average prediction of signal strength in a large area, whereas we would also like to capture the fluctuations which would indicate the local mean. So, this local mean, which is the variation of signal strength in a particular direction, however, in the same area, is covered under the model by shadowing. So, as we move further, what we need to look at is certain measurement results. What I will show you is a geographic map of a region. This is belonging to IIT Kharagpur. We have done some measurement campaign over here. So, these red dots as indicates we have taken average readings, we have moved straight down this line. There is a transmitter located in this region. So, we are as if going away from the transmitter, taking readings as a function of distance. So, we keep on doing it. So, basically going back to our figure here, once we do it for one distance, we would repeat the same exercise for another distance across this. We repeat the same exercise at another distance. So, end result what we get is, as we increase the separation distance, at this separation distance there is a certain received signal strength average across the whole area. I move further down, I have done several readings in this area, I get another average reading. As I move further down, my distance has increased. At that distance, I take average reading across the whole area and I get the average received signal strength, and what I get is the average received signal strength as a function of distance, and the slope of d is indicated by NP. So, based on that, what we have done is we have taken one typical example. We have taken readings at one point, at another point, at another point. So, we are increasing the separation distance, and we have calculated this distance of separation from the transmitter to the measuring points, and we kept on moving in the straight line. You can see the field here, and as we move down, the field is here. So, we are moving almost in a straight line, nearly a straight line, and this is the edge of the previous picture. So, we moved straight down and we have measured signal strength up to this point, and when we have plotted the result, the average received signal strength is as indicated by this red line. So, if it was only path loss in nature, we would have expected a straight line in this direction with a particular slope. However, what we have received is fluctuations. So, where signal strength goes down and then again goes up, it could again go down, but on an average there is a decrease across distance. But to cater to this local fluctuations, as we are seeing, we need to improve upon the model which we have discussed till now. Now, this result is again from Rappaport. If you open the book, you will find this particular figure in the book, which represents transmitter receiver separation as a function of distance and path loss in dB, and these are like different values of exponent. So, even if there is like path loss for a particular value of NP as given there are fluctuations about that particular slope. So, we have to find a mechanism in order to capture this model, so that we are able to predict the received signal strength at a separation distance between the transmitter and receiver, and not just look at the area average received signal strength. So, to improve the model over path loss, the path loss as said is the area mean, the shadowing model which is the local mean, the received or the path loss can be written as path loss at D0, that means at the close in reference point D0, plus NP 10 times NP, NP would be the path loss exponent, plus log base 10 of D divided by D0, because D0 is known, plus there is some x sigma. This is the typical notation, x sigma, where the received signal strength is Pt at distance d minus path loss. So, with these two formulas, we would be able to calculate the received signal strength at a distance d. Now, if we compare this particular expression with the one that we had done before, what we would write for the previous expression is P r d and a bar on top. Basically, what we would have is from path loss only indicating the area mean, right. Whereas, when we write P r d, we mean at a distance d, probably at a particular location, what is the received signal strength. Now, this you could also say is like the path loss or the received signal strength at d, plus there is some random fluctuation beyond the average. Now, this random fluctuation x sigma has been found from measurements to match a Gaussian distributed random variable in the dB domain. So, that means, when the received signal strength is measured in decibels, under such conditions this sigma follows a Gaussian distribution, and this sigma, which is indicated below in x, sometimes it is also referred to as chi, is the standard deviation of this Gaussian random variable and also given in dB. The values of NP and sigma are actually computed from measured values through lot of measurements campaign. One of the typical measurement experiment that could be done is what I have shown in this, but there is extensive amount of measurements from which these values of NP and sigma can be calculated. If we look at typical propagation models, what we would find is if there is path loss on the y axis and separation distance between the transmitter and receiver, there would be a certain slope which is found by the NP or the area mean of received signal strength, and this follows the power law with a factor of, let us say, 3.5 in this particular example. And if we take the shadowing, which is the random component, and the sigma that we have just described, this particular sigma. So, what we have assumed over there is NP is 3.5, and this x sigma or chi sigma, which is Gaussian distributed in dB domain, has the value of standard deviation around 8 dB, as has been shown. So, this is what we are going to get. So, this will result in further fluctuation of signal strength. That means, when you are close to the base station, you would get fluctuations beyond this, where the maximum received signal strength would go even beyond predicted by the average because of the random fluctuation. If you see this model, there is random fluctuation. To support this, we have if we look at this data, so signal strength can actually go above means it did not decrease monotonically, it can go above, and if this is the average slope as pointed by the cursor, it could go below the average. So, there is fluctuation above and below the average, and this is a 0 mean. So, that means the mean is predicted by this part, this is the mean path loss. About the mean, there is fluctuation on the positive side, there is fluctuation on the negative side. So, if there is fluctuation on the positive side in the path loss model, there is fluctuation of received signal strength in the negative side, and vice versa between the path loss model and the received signal strength. So, that means if we have the model here, when you are at a very large distance from the base station, similarly signal strength is going to fluctuate both above the average path loss and below the average path loss. So, what you will find is that the received signal strength would be fluctuating greatly. So, this shadowing effectively increases the dynamic range of the received signal, thereby posing even a bigger challenge for transmitter receiver design for such wireless communication systems. That means, the receivers would require a much higher dynamic range to operate. There are many mechanisms to take control of this, which are typically studied in subjects on mobile communications. So, now if we look at the similar model from 3GPP as we have seen in the previous lecture, again we look at the same model. We did not highlight some parts of this model, which we will now highlight as is seen below. This L loss is having this I plus 37.6, which is 3.76 multiplied by 10 log base 10 of R. I for 2 gigahertz is 128, and I for 900 megahertz is almost 121. So, this particular model you have seen. Now, this model is improved by giving the description about shadowing standard deviation, which is given by 8 dB. So, what you see is this path loss model is further improved or qualified by giving information about the standard deviation of shadowing, which is 8 dB as in this particular model. There are many more details to shadowing also, but this is the minimum thing which we should consider in our calculations of predicting received signal strength. Now, these few slides are again taken from the numbers as given in the book by Rappaport. You will find similar numbers in other books, of course, for different scenarios. Now, this is very specific to the measurement campaign which Rappaport has been reporting in many of his papers and many of papers from other references as well. So, some of the things we will take from this are like metals around at the frequency of 800 megahertz have a loss of around 26 dB, and if you look at the light textile inventory, it has a loss of around 3 to 5 dB. And if you look at some other situations, there would be loss of around 10 to 15 dB, loss from one floor and one wall is around 30 to 40 dB. So, what you see is that when there are obstructions between the transmitter and receiver, there is attenuation which varies depending upon the type of obstruction and the frequency of operation. If we move beyond to certain other references, again from the Rappaport book, what we find is if there is a 5-meter storage rack with large paper products, there is loss of around 6 dB, whereas with metal parts loss around 20 dB, and so on and so forth. There is this floor attenuation factor. When it is through one floor, there is around 12 dB, to 2 floors it is around 18 dB, 4 floors around 27 dB, and so on and so forth. So, what here in this particular slide, again taken from Rappaport as given in the particular book, what we will find is at different frequencies, different values of path loss exponent and standard deviation are reported. For example, in a typical retail store, path loss exponent of 2.2 with a shadowing standard deviation of 8.7. Now, with these two parameters specified, we complete the model through which we can generate samples of received signal strength, which would statistically meet the performance or the measured values as has been obtained. In a grocery store, what we can see is the values would decrease to 1.8. Of course, it depends upon the type of store and the type of locality and the type of things that are kept. What we see is one of the highest is in metal working location, where it is 3.3, and there is also around 3 in office with hard partition, and the values of sigma having a range of around up to 14. It has a low value of around 3. So, what you see that sigma is also having a lot of variations, NP is also having a lot of variations. So, when we are supposed to solve a particular problem, we would be expecting these numbers to be first found out through channel model experiments. Once these numbers are available, then we can do coverage probability analysis. So, to summarize, we can see that the range of sigma is within like 5 to 12 dB and typically around 8 dB. It increases slightly with frequency, as has been reported by some observations, and it is nearly independent of the radio path. That means, it does not depend upon the separation between the transmitter and the receiver. It is for microcells, it has been found to be around 14 to 13 dB, typically in the range of again 6 to 8 and sometimes going to 4.5 dB, and it has also been found to decrease with urbanization or density of scattering. If there is too much, then there is also, it has been found to decrease to 1.3 to 1.8. There is also a method to simulate this shadowing values, which would be added to this path loss exponent. So, basically what we mean by this is, in this formula, how do we get these values of x sigma? Now, this x sigma are basically Gaussian random variables with 0 mean and a particular value of standard deviation. So, these values have to be generated following this distribution. Now, what we can remember is that as we have the separation distance between the transmitter and the receiver, which is given by d, there is path loss, there is shadowing. Now, this shadowing is typically correlated. That means, we do not find abrupt fluctuations of average received signal strength. That means, if we take this particular figure which we had drawn, in this region, we would find slow fluctuation of the local mean. We would not find a sudden high of around 10 dB and within the next 1 meter another dB, because these are all averaging. This is the local mean, as has been, see, this is still a mean. Mean means averaging over a small area. That means, if the readings are averaged over this area, whatever value we get is being captured by shadowing. Whereas, if we average over the whole area, we get the area mean, which is NP. So, there is when you, the moment you do average, there is kind of correlation that is getting added. So, these path loss exponents or these standard these shadow fading values can be they would be correlated, and one way of generating them through simulations would be following this particular model, which is filtered Gaussian noise, where you can say Vk is the Gaussian random variable, and this omega k is the value which is obtained at a particular location or at a particular iteration, and there is a certain amount of memory that is involved, which is basically the correlation parameter, and there is certain amount of randomness which is brought in by Vk, which introduces this Gaussian distribution. This kind of filtered Gaussian noise model, which is followed in order to include correlated shadowing. Now, for our particular course, we do not need all these details of correlated shadowing and so on and so forth. What we can at most use is the path loss exponent and shadowing. Most important to remember is these models provide us with the average received signal strength as a function of separation distance, along with certain random fluctuations. We will be concerned with the signal attenuation only. Once we are studying in mobile communications in a different subject, then you need even more details of shadowing to calculate the boundary coverage probability and so on and so forth. With this, we more or less summarize large scale propagation models. What I would like to point out is to try out some of the things, or to try out few numericals. I would welcome you to visit the site fcmc.iitkgp.ac.in. This is a virtual laboratory which is sponsored by MHRD, and it has been developed. So, one can use it for free There is no price required to be paid. All you require is internet access, browser, and it runs on Java applets. So you have to install Java from the internet. All the hints are mentioned. If you have any difficulty, you can always communicate with the TAs of this particular subject who can help you. So in this particular website, you will find a few examples or a few exercises 1, 2, 3, and 4 and so on. So you can try out these examples yourself, which are tutorials are given in the particular website, which you can read by yourself and you can try them out. There could be some security issues during installation or during trying out the experiment. All detailed instructions are mentioned. So whatever we have discussed in this particular class and the previous lecture, you could try out some of the examples which would help you cover these particular lectures. There are some advanced topics. Again, the references are mentioned in that particular website, as well as tutorials and numericals are worked out. Following them, you can complete a few experiments as well, which is not necessarily part of our discussion. Thank you.